So it is my great pleasure to introduce Mariam Ali. She got her undergraduate degree in the University of Toronto, and then she went on to do a PhD in UC Davis with Andrew Ioannidis and Sharon Ranganathan, who were both really, famous people who work on memory. Then she went to Princeton to do her postdoc with Victor Brown, and from 2017 she's been an assistant professor at Columbia, where she's been doing really well. Last year she was voted as a rising star of the Association for Psychological Science, and also got a NSF Career Award, which is this really competitive and really prestigious award, and it is very well deserved. Mariam works on attention, working memory, perception, and especially she's interested in the function of the hippocampus. She does some of the most interesting work in the field in my judgment at least. And one very interesting thing about Mariam is that beyond her excellent work in science, she also is involved in a lot of things that are outside of science itself. So she's a big proponent of normalizing mental illness and making it easier for people to talk about this and to deal with it when they have issues. She has been a big proponent of doing science the right way and dealing with each other the right way. So, for example, she's a big proponent of having a good lab manual. So, for the grad students that you're going to talk to her, she actually has an article on that. You should check it out. And her lab manual is also available in open source for anybody who wants to check it out. So without further ado, let me just turn it to Mariam. Thank you so much for accepting our invitations. And one more thing to say, I will be the moderator for this. So if you have a question, please write in the chat. For questions that I judge that they're immediate, I'll interrupt Mariam myself and I will ask the question. Otherwise, if it seems like a bigger picture thing, then I'll wait until the end and then I'll ask those questions. All right, Mariam, take it away.
So thank you so much for having me here today, and thank you, Dovi, for the very kind introduction. And I'm really looking forward to telling you about some of my lab's work exploring interactions between attention and memory in the hippocampus. I want to start off by having you all imagine that you're faced with a really big problem. For example, how to try to understand the brain. So it can be really useful if you tried to simplify that problem by breaking it up into a set of smaller problems and then tackling each of those in isolation. And that's traditionally how cognitive neuroscience research has progressed. For example, you might be really interested in visual perception, so you might choose to study occipital cortex or ventral temporal cortex. Or maybe you really care about long-term memory, so maybe you study the hippocampus or the medial temporal lobe cortex. Or alternatively, you might want to focus on attention, and so you turn to the prefrontal cortex. And this approach has been incredibly useful in generating lots of very important insights about the mind and brain. But in my lab, we try to challenge these boundaries. So for example, is it really the case that there is an abrupt transition in the brain between perception and memory, or can perception critically depend on so-called memory systems like the hippocampus? Does the reach of attention also extend to these so-called memory systems? And the approach that I want to argue for, and my lab's general philosophy, is that we can better understand the mind and brain if we focus on how the representations of any given brain area can allow that region to very flexibly contribute to many different aspects of cognition. So in my talk today, I hope to be able to convince you that the hippocampus, rather than being a dedicated memory system, is one such brain area whose representations, and particularly its flexible relational representations, allow it to critically contribute to attention and perception, as well as memory. So this talk is about attention, perception, and memory. So before I dive in, I want to give a quick overview of how these different aspects of cognition interact with one another and how they operate. So I want you to imagine that you're in this art museum and you find that you're surrounded by paintings. But there's also other things. So there's decorations on the wall and there's different pieces of furniture. So how are you able to process such a complex environment? Well, if you're interested in paintings, you might choose to direct your attention to a specific painting on the wall. And once you do that, it'll change the way that you perceive it by enhancing the representation of its features in your visual cortex. And attention will also affect your memory. We're more likely to remember things that we pay attention to than things that we don't. So attention, perception, and memory all interact, but what I want to challenge is the idea that they depend on separate dedicated systems in the brain and operate with different functional principles. And instead, I want to argue that common functional principles and common neural representations can help us understand many different aspects of cognition. And I'll do that by using the hippocampus as an example and show how its flexible relational representations can be used in the service of attention, perception, and memory. So to that end, I'll go over 3 lines of research. In the first part of my talk, I'll ask, how does attention create memory? In the second part of my talk, I'll ask if the hippocampus can play a necessary role in attentional behavior, and if so, how? And then finally, I'll ask how our long-term memories can guide attention. So first, how does attention create memory? Well, we know that attention is critical for memory at a behavioral level. So the way that you direct your attention will influence what you remember later on. But how does that happen mechanistically, and how does that happen in the brain? Well, there are at least 2 potential routes by which attention might influence memory. So first, we know that attention has really strong effects on the visual system. So if this is the flow of information from occipital cortex to ventral temporal cortex, then one possibility is that attention will simply strengthen these representations, making them more likely to be transmitted to the hippocampus and then encoded into memory. But an alternative possibility is that attention might directly modulate the hippocampus itself. So in a couple of different studies, we first asked, how does attention modulate the hippocampus? And if it does, what are the implications of that for what we encode into our long-term memory? So how does attention modulate the hippocampus? Well, surprisingly, we know relatively little about that because most studies of attention will tend to focus on sensory cortex. And there, the classic finding is that attention will serve to increase the overall level of activity in brain areas that code for attended features or attended locations. So higher levels of activity for attended versus unattended information. So some studies have taken that logic, which we know is really successful in sensory systems, and they've applied it to the hippocampus. But surprisingly, they found that attention doesn't seem to modulate the overall level of activity in the hippocampus during online processing. However, based on some work in animal models, we hypothesized that attention might do something distinct in the hippocampus, and that's stabilize patterns of activity. So the idea is, if this is a pattern of activity in your hippocampus when you're in a particular attentional state, this pattern might be more likely to occur across various instances of that same attentional state compared to if you were to switch to a different attentional state, in which case the pattern of activity might be relatively distinct. So we wanted to look for state-dependent patterns of activity in the hippocampus. So to look for these state-dependent patterns, we designed a task that we've been calling the art gallery task. And the idea here was to try to manipulate attention to relatively high-level, abstract, and relational features, which we know from memory research are a really important aspect of hippocampal representations. So when I say relational features, what I mean are representations of multidimensional components of any given experience, So in these studies, that will be representations of visuospatial associations. So this is what the task looked like. On every trial, we had participants view a base image, which was a room. It was rendered in 3D, and it had multiple different pieces of furniture, different angles in the walls, and also a single painting. And then we told people before each trial whether they should attend to the art or to the room. So on art trials, their job was to attend to the artistic style of the painting, so things like the use of color and the type of brushstrokes. And on room trials, they had to attend to the spatial configuration of the room, so the arrangement of the furniture and the angles of the walls. After the space image, participants viewed a search set of 4 other images. On art trials, they had to search through the search set to see if they could find a painting that could have been painted by the same person who painted the painting in the base image. And the matching painting would be similar in terms of its artistic style, but not necessarily its content. On room trials, participants had to search through the search set to see if they could find a room that had the same spatial layout as the base image, but viewed from a slightly different perspective. And critically, everything else about the base image and its matching room was different, so we changed the wall colors, chairs were swapped with different chairs, tables with different tables, and so on, but the arrangement of those elements was the same. And then finally, at the end of the trial, participants had to respond yes or no as to whether they found a match. So there are 2 important aspects of this design that I want to bring your attention to. The first is that we used the same exact stimuli in both attentional states, and this allows us to isolate effects in the hippocampus that are related to the participant's top-down attentional state rather than differences in bottom-up stimulation. And second, low-level visual information was not especially useful in either task, and we thought that would make these tasks more likely to recruit the abstract relational representations of the hippocampus. So specifically, the art task might draw on relational representations because participants had to attend to multidimensional components of the painting, so things like the use of color and the type of brushstroke, and then relate those features to other paintings. And the room task might require relational representations because participants had to attend to multidimensional features of the rooms, so the arrangement of the furniture and the angles of the walls, and relate those features to other rooms. So to give you a better sense of the task, here are sample room matches. So these 2 rooms have the same spatial layout from a slightly different perspective. You can see that they both have a painting with a desk to the left and a couch to the right. In this case here, you've rotated a little bit to the left, so now you can see a bookcase, but you can no longer see the window. And here are sample art matches. So these 2 paintings are painted by the same artist. You could see similarities in terms of the choice and use of color and the overall impressionist style. So to look for state-dependent activity patterns, we had people do these tasks while they were being scanned with high-resolution fMRI, and we also acquired high-resolution structural images on which we manually segmented different subfields of the hippocampus as well as medial temporal lobe areas that feed into the hippocampus. So in medial temporal lobe cortex, we had regions of interest for entorhinal cortex, perirhinal cortex, and parahippocampal cortex. And in the hippocampus, we had regions of interest for subiculum, CA1, and then a combined region of interest for CA2, CA3, and dentate gyrus. And of all of these regions, we were most interested in CA2-3 dentate gyrus because prior studies have linked activity in this region to memory encoding. So to look for state-dependent activity patterns, for each of these regions of interest, we extracted the pattern of activity for every trial in the experiment. So for every art trial and for every room trial, we extracted the pattern of activity. And then we correlated these activity patterns as a function of the participant's attentional state. So we correlated art trials with other art trials and room trials with other room trials. And together that gave us a measure of how similar activity patterns are when attentional states are the same. And the comparison is if we correlate art trials with room trials, and that gives us a measure of how similar activity patterns are when attentional states are different. So if a region of the brain contains attentional state dependent activity patterns, then you would expect higher pattern similarity, higher correlations for trials of the same state compared to trials of different states. And that is exactly what we found in the hippocampus. So each hippocampal region of interest showed these state-dependent activity patterns with higher pattern similarity for trials of the same state compared to trials of different states. So attention does modulate the hippocampus. It creates these state-dependent activity patterns, and this might have been missed in prior studies because they only looked at the overall level of activity. So we next directly compared the two attentional states, and we found that in the hippocampus, pattern similarity was much higher for the room state compared to the art state. So room-to-room correlations were higher than art-to-art correlations. And this raised the possibility that the hippocampus might have a special role in spatial relational attention. So we found these results encouraging, but if attention modulates the hippocampus, then this modulation should also be linked to attentional behavior. And in fact, we found in CA23 dentate gyrus that individual differences in how stable the pattern of activity was in the room task predicted behavior on the room task. And this correlation here was selective in a number of different ways. So first, this was the only region of the brain where attentional modulation predicted behavior. It was also selective to the task. So pattern similarity on the room task predicted behavior on the room task, but didn't predict behavior on the art task. And it was also selective to the measure of pattern similarity because the overall level of activity didn't predict behavior. So attention modulates the hippocampus and in a way that is meaningful for online attentional behavior. So from that first study, we found the signature of attention in the hippocampus, which was the creation of state-dependent patterns of activity. We then conceptually replicated this effect with a very different paradigm in which we examined attention to size relations, spatial relations, and temporal relations. And then in a follow-up study, we examined the consequences of these attentional states for subsequent memory. And here we found that the quality of hippocampal attentional states during encoding predicted memory for goal-relevant information. So on trials in which the hippocampus was in a good art attentional state during encoding, participants were subsequently more likely to remember unique visual features of the paintings that they were looking at. And on trials in which the hippocampus was in a good room attentional state during encoding, participants were subsequently more likely to remember unique details of the rooms that they were looking at. So far, we have some insight into how attention can create memory. Attention can change the state of the hippocampus, and the hippocampus can then prioritize goal-relevant or task-relevant aspects of the environment for encoding into episodic memory. But of course, the work that I've shared with you so far has come from fMRI, and we know that fMRI can only provide correlational evidence. So if I want to make the argument that the hippocampus plays an essential role in some aspects of attentional behavior, then I have to examine what happens to attention when the hippocampus is damaged. And my former research assistant, Nick Ruiz, did exactly that. So if the critical aspect of hippocampal function is its relational representations, then hippocampal damage should impair relational forms of attention. So to test the hypothesis that the hippocampus might be critical for relational attention, we used a modified version of the art gallery task I've been telling you about. We simplified it so there were only 2 images on each trial, and that was to make the task more feasible for patients with hippocampal damage. So we had 4 types of trials. The first 2 are the trials that you're already familiar with, and the purpose of these trials was to try to engage the relational representations of the hippocampus, and I'll refer to these as similar trials. So on each trial, participants viewed 2 images, which were these rooms rendered in 3D with multiple pieces of furniture, different wall angles, and a single painting each. On similar art trials, participants had to judge if the two paintings could have been painted by the same artist, like these two paintings here. And on similar room trials, they judged if the two rooms had the same spatial layout from a slightly different perspective, like these two rooms here. And we know from our past fMRI studies that the hippocampus can discriminate between these two attentional states and that its activity predicts behavior. The other trial types were control trials, which we did not expect to require the hippocampus because they place fewer demands on relational processing, and I'll refer to these as identical trials. So again, individuals viewed two images on each trial, but this time they simply had to detect repetitions of identical paintings, like here, or repetitions of identical rooms, like here. And the idea is that this can be accomplished really easily on the basis of representations in visual cortex without any need for hippocampal relational processing. So we had similar trials and identical trials, and within each of these, we had room attention and art attention. So what did we predict? Well, one hypothesis is that the hippocampus is critical for any task that requires relational representations, and that would be consistent with many different models of hippocampal function. So if that's the case, then you might expect hippocampal damage to impair performance on similar room trials and similar art trials, while leaving performance on the identical trials unaffected. But an alternative hypothesis is that hippocampal damage might only impair performance on the similar room trials, because in our past fMRI studies, we've always found that the hippocampus is much more strongly modulated by the similar room task and predicts behavior best for the similar room task. And that would also be consistent with models of hippocampal function that emphasize its importance for spatial processing or spatial cognition. And it would also be consistent with studies that have found that hippocampal damage can impair the perception of complex scenes, but not complex objects. So to test these hypotheses, Nick tested 7 patients with medial temporal lobe damage and 14 healthy Asian education matched participants. So here I'll show you the data for the healthy participants as the filled in circles and data for the patients as the open shapes. One patient had bilateral hippocampal damage following a hypoxic event. He'll be the open diamond. And the remaining patients had unilateral temporal lobectomies for the treatment of intractable epilepsy. They had damage to the hippocampus and medial temporal lobe cortex on one side of the brain. The ones with the right hemisphere damage are the open triangles, and the ones with the left hemisphere damage are the open circles. And I'll show you behavior in terms of A prime, which is a non-parametric version of D prime. So it's a measure of behavioral sensitivity, where 1 indicates perfect performance and 0.5 indicates chance performance. So we found no difference between the healthy participants and the patients on identical art trials. And there was also no group differences on the identical room trials. Intriguingly, the patients were not at all impaired on the similar art trials, but they were significantly impaired on the similar room trials, and in fact, their performance wasn't different from chance. And because all of these patients had hippocampal damage, and the damage outside of the hippocampus varied across patients, we can infer that the hippocampus, or medial temporal lobe more broadly, does play an essential role in online spatial relational attention or perception. So far we have some preliminary evidence that the hippocampus might play a necessary role in some components of attentional behavior, and particularly spatial relational discriminations. This second part of my talk had a 2-part question, so we've hopefully answered the first part, but the second part now is how. So how does the hippocampus come to play a role in attention or perception? So now I'd like to tell you about some pharmacological studies in my lab in which we're trying to determine the neuromodulatory mechanisms of attention in the hippocampus. And this is work done by Nick Ruiz and Monica too. So we were interested in this question because at any given moment, there can be competition in the hippocampus between internal and external sources of information. And specifically, there can be competition between input to the hippocampus about the external world and memory retrieval mechanisms that might bias the hippocampus toward internal information processing. So for example, imagine that you're in an art museum and you choose to direct your attention to a specific painting on the wall. But once you do that, the visual features of that painting might trigger memory retrieval of some associated information. So if you want to suppress memory retrieval in order to better focus your attention on the visual details of the painting, you need to somehow bias hippocampal processing toward the external environment. And it turns out that acetylcholine can do exactly that. So to better understand how cholinergic modulation might enhance hippocampally mediated attention and perception, we first have to consider the hippocampus in a little bit more detail. So input from entorhinal cortex to the hippocampus is important for conveying information about the outside world and encoding new memories, while recurrent connections in hippocampal subfield CA3 are important for retrieving memories. Acetylcholine enhances afferent input from entorhinal cortex to the hippocampus and suppresses excitatory recurrent connections in CA3. So this should have the effect of biasing hippocampal representations toward the external environment, which has to occur for externally oriented attention and perception. So acetylcholine should stabilize hippocampal representations of the external world, and in that way improve attention and perception on relational attention tasks like the ones that we've used previously. So our specific hypothesis was that if cholinergic modulation enhances externally oriented states in the hippocampus, then cholinergic modulation should improve performance on attention and perception tasks that require the hippocampus. And specifically, cholinergic modulation should improve performance on the similar room trials because those were the ones that we've shown in our patient studies to require the hippocampus. I'm noting here that we initially hypothesized that performance on the other trial types would be unaffected by cholinergic modulation, but that certainly doesn't have to be the case, and I'll return to that in a little bit. So to test this hypothesis, we had people do the same exact task that we used with the hippocampal lesion patients, but this time we had a pharmacological manipulation. So we had people do this task while they were on a cholinergic agonist, and again while they were off a cholinergic agonist, to see how cholinergic modulation affected their behavior. So what we did is we found people who voluntarily ingest cholinergic agonists all the time, and that's cigarette smokers. Because they give themselves nicotine, we didn't have to jump through any hoops with the IRB, so it worked out really great. So what we did is we had nicotine cigarette smokers come into our lab for 2 sessions. Both were first thing in the morning. One session was their on session, for which they smoked right before coming into our lab, and then they did our task with the similar and identical art and room trials. For their other session, with the order counterbalanced, of course, they abstained from cigarette smoking for at least 12 hours before doing our task. We asked them how many cigarettes they smoked to note compliance. People reported smoking 1 to 3 cigarettes for their on session and not smoking at all for the past 12 hours for their off session. But of course, we didn't just take their word for it. We also had them breathe into these carbon monoxide monitors. So carbon monoxide ppm, or parts per million, provides a measure of how recently or how much someone has smoked, and it's a standard measure in studies of cigarette smoking. And importantly for us, carbon monoxide levels are fairly highly correlated with nicotine levels in the blood. So we made sure that carbon monoxide ppm was higher for the on versus off session. And again, our prediction was that if cholinergic modulation enhances hippocampally mediated attention and perception, then nicotine cigarette smokers should perform better on the similar room task when they are on versus off nicotine. So here I'll show you performance for the off and on nicotine sessions, with performance again being measured as A prime. We found no difference between the off and on smoking sessions for the identical art trials. There's also no difference between sessions for the identical room trials, and also no difference between sessions for the similar art trials. But then, and contrary to our hypothesis, there was also no difference between the on and off smoking sessions for the similar room trials, so we found null effects here across the board. But that said, the on versus off comparison is a little bit coarse, and we do have more precise information about people than whether or not they smoked, because we have their carbon monoxide ppm levels, and those tell us how much or how recently they smoked. So if cholinergic modulation enhances attention, then individual differences in carbon monoxide levels should be related to performance enhancements. So to test that, we calculated two measures for each individual. First, we took their carbon monoxide ppm difference between their on and off smoking sessions, and that means that even if someone cheated and smoked prior to their off session, that difference score would still tell us how much more they smoked for the on versus off session. And we also calculated their A prime difference between the on and off smoking sessions. So more positive values here would indicate a greater performance enhancement on nicotine. So if cholinergic modulation enhances hippocampal attention and perception, then the individuals with the highest carbon monoxide ppm difference should show the greatest performance enhancement, specifically on the similar room trials, and that's exactly what we found. Carbon monoxide ppm differences didn't predict performance enhancements on any other trial type. So this result was consistent with cholinergic modulation of hippocampally mediated attention and perception. So to return to this slide, our hypothesis was partly correct, but partly wrong. We didn't observe general performance enhancement on versus off nicotine on the similar room trials, but we did observe a monotonic improvement on this trial type as a function of more nicotine smoking, and that's still consistent with cholinergic modulation of hippocampal attention. We did not observe cholinergic modulation of performance on any other trial type, but that certainly didn't have to be the case. We know that nicotine acts throughout the entire brain, and it can enhance processing in visual cortex. So the null effects that we saw on these other trials has to be investigated further. So to briefly summarize the second part of my talk, we first found the hippocampus can play a necessary role in some aspects of attentional behaviors, and particularly spatial relational discriminations. And second, we found that cholinergic modulation may enhance this form of attention or perception. My talk so far has considered attention in a pretty limited way, so attention in situations in which we just told people with some kind of explicit instruction how they should be paying attention. But that's not typically how attention operates in the real world. In the real world, it's really rare to receive moment-by-moment instructions on how you should be paying attention, and instead, our attentional states are often guided by our memories of past experiences. So now, in this last part of my talk, I want to tell you about some work in my lab related to how our long-term memories can guide attention. So I first want to consider these forms of attention in a little bit more detail, and I want you to imagine that you're in a situation where you're driving to one of your favorite art museums, which in my case would be the Barnes Foundation. So you might see a sign, and that provides an external and explicit environmental cue to pay attention to the right in order to find the art museum. But alternatively, you might be driving down the street and there is no sign, so you instead have to call on your memory for the buildings you drove past to figure out if you're on the correct street, which direction you came from, and then use that to infer whether you should attend to the left or to the right. So the basic idea here is that our attentional states can be guided either by external cues in the environment or by our internally retrieved memories. Kia Nobre and her colleagues have shown that memory-guided attention compared to environmentally cued attention is associated with increased levels of activity in the hippocampus. And this increased hippocampal activity from memory-guided attention is apparent as soon as information from memory is available, and even before an attention task starts. The idea is that you can use your retrieved hippocampal memories to bias your attention one way or the other, and the biasing process can happen even before an attention task begins. We also know that hippocampal activity patterns can represent online attentional states. So the content of hippocampal representations can reflect attentional states that are currently active or currently in play. And finally, a rich body of work has shown that the hippocampus is important for many different aspects of memory-guided behaviors, perhaps through its interactions with the medial prefrontal cortex. So together, these lines of work suggest that the hippocampus, perhaps with MPFC, might be important for guiding attentional behaviors on the basis of memory. So in this study, we asked, how do the hippocampus and MPFC support memory-guided attention? So to address this question, my former postdoc, Arben Gonsalli, compared attention in two tasks that differed only in their demand to use memory to guide attention. We first expected to be able to replicate past studies in showing that hippocampal activity should be higher for memory-guided compared to environmentally cued attention. And given the importance of hippocampal MPFC interactions for memory-guided behavior more generally, we also expected that MPFC would show higher levels of activity for memory-guided compared to environmentally cued attention. But the problem with this is that enhanced overall activity is very ambiguous in that it can't by itself tell us how a brain region might be contributing to memory-guided attention. So for example, it could be the case that the hippocampus just retrieves memories, and then other brain areas use that information to guide attention. Or it could be the case that the hippocampus can actually represent the attentional goal itself. So if we were to go back to that driving example, the difference would be between the hippocampus retrieving a memory that the art museum is on the right versus the hippocampus representing an attentional bias to the right-hand side. And because we know from our past studies that the hippocampus can represent online attentional states, then it's very possible that it can also represent attentional states when they're retrieved from memory. So to examine that hypothesis, we used representational similarity analyses to test the prediction that the hippocampus and MPFC will prepare for upcoming attentional states when those attentional states are selected on the basis of memory, and that they'll prepare by actually representing the attentional state that is going to be used in the future. So going back again to that driving example, the idea is that hippocampal and MPFC activity patterns would contain information about a rightward attentional bias, if that's what memory tells you that you should do, and even before you start attending to the right. So to test these hypotheses, Arben designed a memory-guided version of the art gallery task that you're very familiar with by now. So in this memory-guided version, we first had participants learn a set of stay and switch cues, and these cues told them whether during the subsequent attention task, they would have to stay in the same attentional state on the following trial or switch to the other attentional state. So participants learned an art stay cue and an art switch cue, and a room stay cue and a room switch cue. And these stay and switch cues would only ever appear in the attended dimension. So that means the art stay and switch cues would only appear on trials where art is attended, and room stay and switch cues would only appear on trials where rooms are attended. So to be more concrete, here's a task that you're already very familiar with. Participants viewed this base image followed by a search set, and their task was to look for either paintings that could have been painted by the same artist or rooms with the same layout from a different perspective. But the new thing now is how this attentional cue was selected on each trial. So on the very first trial, participants were free to choose what they wanted to attend to, art or room. So say here the participant chose room. But after the first trial, they had to monitor the search set for stay or switch cues, which could appear anywhere in the search set. and then they had to use the stay or switch cue to select their attentional state for the following trial. So this is an example of a room trial, and there's a room stay cue. So that tells the participant that they have to stay in the same attentional state for the following trial. So in the following trial, they should select room as their attentional state. Alternatively, this trial could have contained a switch cue, which tells the participant that they have to switch to the other attentional state for the following trial. So in the following trial, they should select art as their attentional state. So this memory-guided task requires people to remember the stay and switch cues and what they mean in order to be able to select their attentional states. The comparison condition was the art gallery task we've used previously, which now I'll call the explicitly instructed condition. And this condition is explicitly instructed because the attentional cue was randomly assigned at the beginning of each trial in the form of an explicit instruction. So pay attention to room or pay attention to art. So to briefly summarize the tasks, they had identical stimuli and they had identical motor demands. The only difference was the memory-guided task required people to memorize the stay and switch cues and their meaning in order to select their attentional states. So we first examined univariate activity for the memory-guided and explicitly instructed conditions, and consistent with our hypotheses, we found that both hippocampus and MPFC showed higher levels of activity for memory-guided compared to explicitly instructed attention. Additionally, individual differences in how much hippocampal activity was enhanced by memory-guided attention were correlated with individual differences in how much MPFC activity was enhanced by memory-guided attention. And this suggests that these two regions might be working together or at least engaged in similar functions. So with this result in hand, we next wanted to establish exactly how these regions might support memory-guided attention. And again, we expected that these regions would represent upcoming attentional states, primarily when they were guided by memory. So here's how we tested that. As a brief reminder, this is a trial structure that you're already familiar with. And now what I'll do is break it down into two main components. The image period is when the images are on the screen and participants are actively attending to artistic style or room layout. The orienting period is when participants are pushing a button to initiate the trial and seeing the attentional cue. In the explicitly instructed condition, participants simply have to push 1 or 2 to start the trial, then the attentional cue is randomly assigned. And in the memory-guided condition, participants have to select art or room as their attentional state based on their memory for the preceding trial. So we predicted that during this critical orienting period, that activity patterns in the hippocampus and MPFC will resemble the attentional state that is coming up in the image period, and primarily when that attentional state was guided by memory. So here's how we tested that. First, in the hippocampus and MPFC, we obtained mean patterns of activity for the art and room attentional states from the image periods, and I'll call these templates for the two attentional states. And these templates tell us what brain activity generally looks like when participants are actively attending to artistic style or room layout in the 3D rendered images. We then obtained activity patterns for each individual orienting period, and we correlated the orienting period activity patterns with the attentional state templates from the image periods. So say this is an orienting period in which room is the attentional cue, whether it was selected by the participant or randomly assigned. We would correlate this orienting period activity pattern with the same state template, which in this example would be the room template. And we would also correlate this orienting period activity pattern with the other state template, which in this example would be the art template. And then finally, we'd compare these correlations to one another. So if the correlation with the same state template is higher than the correlation with the different state template, that would tell us the activity patterns in that brain region during the orienting period resemble the upcoming attentional state more than the other attentional state. So it's a type of preparatory signal. And again, we predicted that hippocampus and MPFC would show that effect, primarily when attentional states were guided by memory. So here I'll show you the correlation with the same state template minus the correlation with the different state template. So more positive values here indicate more evidence for the upcoming attentional state, and more negative values indicate more evidence for the other attentional state. We found that in the hippocampus, for the memory-guided task, the activity patterns during the orienting period did resemble the upcoming attentional state more than the other attentional state. This effect was also seen when attention was explicitly instructed. However, the effect was significantly stronger when attentional states were guided by memory. In MPFC, we found activity patterns during the orienting period resembled the upcoming attentional state more than the other attentional state for both the memory-guided and explicitly instructed conditions, but here there was no statistically significant difference. So the hippocampus and MPFC prepare for upcoming attentional states, and they prepare by actually representing the attentional state that has to be used in the future. And in the hippocampus, this preparation was significantly stronger when attentional states were guided by memory. So how does memory guide attention? Well, we first found that memory-guided attention is associated with increased levels of activity in the hippocampus and in MPFC. These effects were correlated across individuals, suggesting that these regions might be working together or at least engaged in a similar function. And we then found that hippocampus and MPFC prepare for upcoming attentional states, and in the hippocampus, this preparation was stronger for attentional states that were guided by memory. So to briefly summarize my talk, I first showed you that attention stabilizes patterns of activity in the hippocampus, and the stability of these representations predicted both online attentional behavior as well as successful encoding into episodic memory. We next found that the hippocampus or medial temporal lobe more broadly might play an essential role in some components of attentional behavior, and particularly spatial relational discriminations. And we also found that cholinergic modulation may enhance this form of attention or perception. And then finally, we found that hippocampus and MPFC are modulated by memory-guided attention and prepare for upcoming attentional states. So I've presented a few studies on the interplay between attention, perception, and memory. So now I just want to conclude by revisiting the point I made at the very beginning of the talk. Again, I think it's really important to divide up the brain into distinct components and analyze their function in isolation. But of course, we know that these components are all linked in order to guide behavior. So I think one very fruitful way of doing research moving forward is to think about the representations of any given brain region and how those representations can allow that region to flexibly contribute to many different components of cognition. So my talk today, I hope I've managed to convince you that the various representations of the hippocampus allow it to critically contribute to attention and perception, as well as memory. So of course, I'd like to thank my lab, particularly Nick Ruiz, Monica Tu, and Erengan Sully, who did the work I told you about today. You can also check out our lab mascot, Theo, who makes substantial contributions to everyday science. Also like to thank my various funding sources and of course you for your attention and your perception and your memory. And I'm happy to take any questions.
All right, here's some clapping from one person. Thank you, Mariam. That was wonderful.
Sure.
So we have a couple of questions. I think it would be best if I just let the people who ask them on the chat ask them directly. Audrey, you asked first. Would you be willing to do that?
Great talk, and thanks for doing this. I know it's awkward and not as great as having you here, but yeah, I just had a couple questions, but I'll ask one because I don't want to, take over other people's time. I was just wondering about the nicotine study, and it's nicotine's a neuromodulator and it can affect other neurotransmitter systems. And so I was just wondering if you had any thoughts about the other neurotransmitters that might be involved here besides acetylcholine.
Yeah, that's a really good question. By doing the nicotine study, we had to balance kind of two components. One is the ease of doing the study versus the straightforwardness of the interpretation. So double-blind, highly controlled pharmacological studies are very difficult to do, and it was something that I was advised to not do pre-tenure. So this was a way for us to kind of dive into something that I'm very interested in and get some preliminary looks at it. But of course, even highly controlled pharmacological studies would not be able to tell whether it's nicotine per se having an effect on acetylcholine receptors that's critical, or through some indirect effects that happen afterwards. So the results lined up really nicely with what we'd expect based on computational models and highly controlled studies in animal models. So it fit the interpretation from that, but yeah, we wouldn't be able to rule out whether the effects were instead indirectly influencing other neurotransmitter systems rather than having the direct effect through nicotine. It's possible that we could gain traction in that by doing magnetic resonance spectroscopy or other studies that might allow us to look at cholinergic activity in vivo, but from this study, we can't rule out other potential effects.
Audrey, how about you ask your other question as well now, I think, while you're on screen?
Okay, sure. And the other question I had was, if I saw it correctly, in the eLife paper, you've got the medial PFC and the hippocampal individual differences. It looked like there was a lot more variability in the hippocampal response, the pattern, yeah.
Yeah, that's right.
And then no, it wasn't. It was the same different subtraction. It just looked like the MPFC difference was super clustered together. Yeah, I think this is it. And I was just wondering if you had any thoughts about it, because it seems like that might be important for differentiating what they're doing. I don't know. Just
Yeah, that's an interesting question. We hadn't really thought about characterizing the variability, partly because it could also be due to maybe uninteresting factors like the quality of the signal that we're getting, or like how closely we can get a match between the preparatory activity and the templates. Offhand, I don't remember whether hippocampus just had noisier signals overall. So I think if you just examined activity patterns during the attention task itself, I'm pretty sure the activity patterns in the hippocampus were just less stable from trial to trial than those in MPFC. So it could reflect something about the signal or the stability of the pattern during the attention task itself. But we could look into that a little bit more to see whether controlling for the variability during the attention task itself might reveal some differences there. We predicted that MPFC would also show greater preparation for the memory-guided task. We didn't see that at all, and so we've been kind of thinking about why that difference might arise, but we haven't dived into whether the variability across regions might also offer some clues into that. But that's a good idea.
So his question is, how do you dissociate orienting period activity from image period activity? This is for the third part.
Yeah, that's a really good question.
Yeah.
We went through a lot of trouble to try to do that. There's some things I would have done differently in hindsight, but I can tell you a little bit of the things that we did. So one major thing that we did is that we never compared orienting period and image period activity patterns from the same run. So the image period templates were always from different runs of the task compared to a given orienting period activity pattern, and that reduces some of the high within run correlations that you see in fMRI. We also calculated this templates across different combinations of runs to rule out other potential confounds. There's also jitter here because this period here was self-paced. People initiated the trial at their own rate, so that added some jitter. And also this period here where the attentional cue was on the screen was also jittered. And then another thing we did is that when we compared these activity patterns to these, we took out TRs that were the most overlapping. So we excluded the last TR of the orienting period and the first TR for the image period. And we also took out the last TR of the image period because otherwise overlap between this pattern and this pattern could be driven by the word, which would not be at all what we're interested in. And then finally, we also did whole brain searchlight analyses. If the if the effect was a part of just a confound or an artifact of autocorrelation, then you might expect that regions throughout the brain would show the same effect, but we did not see that. The effect was highly selective. And one other thing I'll mention is that people on average initiated the trial faster for the explicitly instructed versus memory-guided conditions because this is just an easier decision. So there should be slightly more autocorrelation for the explicitly instructed condition, but of course for the hippocampus, we found greater preparation for the memory-guided condition. So all that together convinced us and convinced the reviewers that it wasn't simply due to overlap between the orienting and image periods, but we still would like to do a version of this maybe with EEG or again with fMRI with even greater separation between the orienting period and the image periods. But yeah, that's something that we worried about a lot and tried to control with as many different ways as we could.
I think that was great, Mariam. Thank you very much for a really interesting talk, and Davi for moderating. Okay.
Yeah. Thank you so much.
Thank you.